The edge of the universe is not where things end. It is where things stop making sense. For decades, scientists believed they had reached the ultimate boundary, a limit beyond which nothing could be seen, measured, or understood. A final horizon, but now something unexpected has begun to shake that belief. Subtle signals, strange patterns, clues that suggest the edge is not just a limit, it may be pointing to something far bigger. In this video, you will learn what the observable universe really is, why it has a boundary, and why that boundary might not be the end at all. You will discover the hidden details most people never hear about, the strange anomalies that scientists still cannot fully explain, and the unsettling possibility that everything we can see is only a small fraction of reality. Stay with me until the end, because the final idea may completely change how you think about the universe, space, and even existence itself. Right now, everything you've ever seen in the night sky exists inside something called the observable universe. This includes every star, every galaxy, every black hole, and every particle of matter that light has revealed to us. It sounds vast, and it is. The observable universe stretches about 93 billion light years across. That number is so large it is almost impossible to understand. Yet even that enormous size is only part of the story. The observable universe is not the whole universe. It is only the part we can see. This boundary exists because of one simple rule. Light takes time to travel. When you look at distant stars, you are not seeing them as they are now. You are seeing them as they were in the past. Some of that light has been traveling for billions of years just to reach your eyes. In a sense, looking into space is like looking back in time. But here is where things become strange. There is a limit to how far we can look back. A point where light from beyond has not had enough time to reach us since the beginning of the universe. That point creates a kind of cosmic horizon beyond it. There may be more galaxies, more stars, even entire regions of space, but their light has not reached us yet. And it may never reach us. This is because the universe is not just expanding, it is accelerating. Space itself is stretching. Galaxies are being pushed away from each other faster and faster. At great distances, this expansion becomes so strong that light can never cross it. Even if a galaxy shines forever, its light will never arrive here. It is not because the light is weak. It is because space in between is growing too fast. This creates a strange and unsettling truth. There are parts of the universe that are permanently hidden from us, not because they are small or faint, but because the rules of physics place them forever out of reach. For a long time, scientists accepted this limit. They believed that beyond the observable universe, there is simply more of the same, more galaxies, more empty space, more matter arranged in similar patterns. The idea felt safe, logical, predictable, but that assumption is now being questioned. Because when scientists look closely at the oldest light in the universe, they see something unusual. This ancient light is called the cosmic microwave background. It is the afterglow of the Big Bang, a faint signal that fills all of space. It is often described as a snapshot of the universe when it was only about 380,000 years old. By studying this light, scientists can learn how the universe began and how it evolved. And hidden inside this ancient signal are patterns that do not fully make sense. There are regions that appear slightly warmer or colder than expected. There are alignments that seem too organized to be random. Some scientists have even noticed structures that stretch across vast distances, far larger than standard models predict. These are not huge differences. They are subtle, easy to overlook. But in science, even small deviations can point to something much deeper. At first, many researchers dismissed these anomalies as statistical noise, random fluctuations that happen in any complex system. But as more data came in, the patterns did not disappear, they remained. And in some cases, they became harder to ignore. This is where the story takes a turn. Because one possible explanation is that these patterns are not coming from within our observable universe at all. They may be influenced by something beyond it. Not empty space, not more of the same, but something fundamentally different. This idea challenges one of the most basic assumptions in cosmology, the assumption that the universe is uniform on large scales, that no matter where you look, the structure should be roughly the same. But if something outside our observable region is affecting what we see, then that assumption may not hold. And that opens the door to a much bigger possibility. The observable universe may not just be a limited view. It may be a small window into a much larger and more complex reality, a reality where different regions of space behave in different ways, where the laws of physics might vary, where entire universes could exist beyond our reach. This is not science fiction. It is a serious area of research. Scientists are using advanced telescopes, precise measurements, and complex mathematics to explore these ideas. They are trying to understand whether the edge we see is simply a boundary of light or something more meaningful, because if the edge contains clues, then it is not just a limit. It is a signal, a hint that the universe is not as simple as it appears. And this raises a deeper question. If everything we observe is only a small part of what exists, then how much are we missing? The atoms in your body were formed inside stars. Those stars exist inside galaxies. Those galaxies are part of a vast cosmic web, and that entire structure exists within the observable universe. But beyond that, there could be far more. Entire regions we will never see. Phenomena we cannot directly measure. Realities that challenge the limits of human understanding. That idea is both exciting and unsettling, because it means that even our best models, our most powerful theories, and our most advanced instruments may only be revealing a fraction of the truth. And now scientists are beginning to take that possibility seriously. So in this video, we are going to explore what lies at the edge of the observable universe. We will break down the science behind this cosmic boundary. We will look at the strange signals that hint at something beyond it. And we will dive into the theories that attempt to explain what might exist outside our cosmic horizon. Some of these ideas are hard to accept. Some may sound impossible at first, but all of them are grounded in real science, real data, and real questions that researchers are trying to answer right now. By the end, you may see the universe in a completely different way. And if you want to explore more ideas like this, make sure to subscribe to the channel and join us as we uncover the deepest mysteries of space and art.
Reality, the edge of the observable universe, is often misunderstood. It sounds like a wall, a final border where everything stops. But that is not true. There's no solid boundary, no cosmic barrier floating in space. The edge is something far stranger.
It is a horizon, not a place you can touch, not a line you can cross. It is a limit created by time, light, and the expansion of the universe itself. Beyond this horizon, space does not suddenly end. It continues, quietly, invisibly, completely out of reach. To understand this, you need to look at how the universe behaves on the largest scale. Space is not static. It is not fixed like a stage where galaxies sit in place. Space itself is stretching, expanding in every direction. This expansion began with the Big Bang and has never stopped. In fact, it is speeding up. This means galaxies are not just moving through space, they are being carried away as space grows between them. Here is where things become unsettling. The farther a galaxy is, the faster it moves away from us. At extreme distances, the speed becomes so great that it exceeds the speed at which light can travel across the expanding space. This does not break the laws of physics, because it is space itself that is expanding, not the galaxy moving through it. And this creates a permanent separation. Light leaving those distant galaxies today will never reach us. Not in a billion years, not ever. The space in between grows too fast. The gap only gets larger. It is like trying to swim across a river that keeps widening faster than you can move. Even more disturbing, some galaxies we can see right now are already gone, in a sense. Their light left billions of years ago when they were closer. Today they have moved so far away that any new light they emit will never reach Earth again. We are seeing ghosts of the past. This means the observable universe is not just limited. It is shrinking in terms of what we can ever access. Over time, more galaxies will fade beyond the horizon. Future observers in our galaxy may see a much darker universe with far fewer visible structures. Right now, we are inside a kind of cosmic bubble. A sphere centered around us, defined by how far light has traveled since the beginning of time. Everything inside this bubble is visible. Everything outside is hidden. But this bubble is not special. It only feels that way because we are at its center. Every observer in the universe has their own observable bubble centered on their position. This leads to a powerful realization. The universe is not centered around us. Our view is limited by where we are and when we exist. There could be vast regions of space filled with galaxies, structures, and phenomena that we will never detect. Some scientists estimate that the total universe could be far larger than what we see, possibly infinite. If that is true, then the observable universe is only a tiny patch in an endless expanse, a small island in a cosmic ocean. And inside this island, every discovery, every theory, every piece of knowledge is based on incomplete information. Because beyond that horizon, there may be patterns, forces, or structures that we have never accounted for. The edge, then, is not the end. It is a limit placed on our perception, and limits like that often hide something much deeper. There is a faint glow that fills the entire universe. It is everywhere, in every direction. It does not come from stars or galaxies. It comes from a time long before they even existed. This glow is called the cosmic microwave background. It is the oldest light we can see, a relic from when the universe was only about 380,000 years old. At that time, the universe was hot, dense, and filled with charged particles. Light could not travel freely. It kept scattering, bouncing in all directions. Then, as the universe expanded and cooled, those particles combined into neutral atoms. Suddenly, light was free to move. That ancient light has been traveling ever since. Today, it appears as a faint microwave signal, almost perfectly uniform, almost the same temperature everywhere. This is one of the reasons scientists believe the universe is smooth and consistent on large scales. But not perfectly. When scientists began to measure this radiation with high precision, they noticed tiny differences, small fluctuations in temperature, differences as small as 1 part in 100,000. At first, this was expected. These slight variations helped form galaxies and large structures later on. But then something unusual appeared. Some of these fluctuations seem to follow patterns, not random noise, not evenly spread variations. There were alignments, regions that appeared to line up across vast distances, structures that stretched farther than standard models predicted. One of the most famous of these patterns is something scientists refer to as the axis of evil. The name sounds dramatic, almost like science fiction, but it reflects a real puzzle. When researchers mapped the cosmic microwave background, they found that certain large-scale temperature variations were aligned along a specific direction in space. This alignment should not exist. According to standard cosmology, the universe should look random and isotropic at large scales. No preferred direction, no special alignment. Yet the data suggested otherwise. At first, many scientists dismissed this as coincidence, a statistical fluke. After all, when dealing with vast amounts of data, strange patterns can appear by chance. But as measurements improved, the alignment did not disappear. It remained. This raised a troubling question. Why would the largest structures in the observable universe show a preferred direction? Some researchers began exploring more radical explanations. They considered the possibility that these patterns were not generated entirely from within our observable universe, that something beyond our cosmic horizon might be influencing what we see. This idea is difficult to test. By definition, anything beyond the observable universe cannot be directly measured, but indirect effects could still leave traces. Subtle imprints, slight distortions in the oldest light we can observe. There are also other anomalies. A region known as the cold spot stands out. It is an unusually large area of lower temperature, much larger than expected. Some studies suggest it could be caused by a massive void, a region with fewer galaxies, but others argue that explanation may not fully account for its size and shape. Then there are hemispherical asymmetries. One side of the sky appears slightly different from the other, not by much, but enough to raise concern, enough to question whether the universe is truly uniform. Each of these anomalies on its own might be dismissed, but together they begin to form a pattern of their own, a pattern of doubt. Are these just random fluctuations that look meaningful because the human mind seeks order, or are they signals? Clues that point to something outside our observable region. If these patterns are not random, then they may be telling us that the universe is influenced by forces or structures we cannot directly see. And that possibility begins to connect with a much larger and more unsettling idea. To understand where these strange patterns might lead, scientists turn to one of the most powerful ideas in modern cosmology. It is called inflation. In the earliest moments after the Big Bang, the universe did not expand at a steady pace, expanded at an extreme rate, faster than anything we see today. In a tiny fraction of a second, space itself stretched violently.
Regions smaller than an atom grew to cosmic scales. This rapid expansion solved many problems. It explained why the universe looks smooth.
It explained why distant regions share similar properties, but it also opened the door to something far more unsettling, because inflation may not have happened just once. Some versions of the theory suggest that inflation is not a single event. It could be an ongoing process, a process that continues in different regions of space, creating new pockets of expanding universes again and again. And so these regions are often described as bubble universes. Each bubble forms when a small part of space stops inflating and settles into a stable state. Inside that bubble, a universe begins to evolve. Matter forms. Galaxies take shape. Time and space behave in consistent ways. But outside that bubble, inflation may still be happening, creating more bubbles, endless pockets of reality, each separate from the others. And here is where things become even more strange. Each of these bubble universes may not follow the same rules. The fundamental constants of physics, such as the strength of gravity or the mass of particles, might be different in each bubble. In one universe, gravity could be stronger. In another, atoms might not form at all. Some universes could collapse instantly. Others could expand too quickly for stars to ever exist. This means our universe might not be special in the way people once believed. It might simply be one of many regions where the conditions happen to allow complexity, structure, and life, a rare combination, but not unique. There is also a deeper implication hidden inside this idea. If these bubbles are truly separate, then they are likely beyond our observable horizon, completely disconnected from our view. Their light will never reach us. Their galaxies will remain forever hidden, yet their existence could still be real. Some physicists suggest that the total number of these universes could be enormous, possibly infinite. A vast cosmic landscape where every possible set of physical laws exists somewhere. In that case, reality is not a single universe. It is a collection of countless universes, each with its own structure, each with its own history, each existing independently, yet all part of a larger system we can barely comprehend. This idea also offers a possible explanation for some of the strange patterns seen in the cosmic microwave background. If our universe formed mere other bubbles, or if inflation created uneven conditions at large scales, it could leave subtle imprints in the structure of space. Not direct evidence, but faint echoes of a much larger reality. The concept of a multiverse changes the scale of existence completely. It removes the idea of a single, complete universe and replaces it with something far more complex, a layered reality, a system where what we observe is only one outcome among countless possibilities. And if that is true, then the edge of our observable universe is not just hiding empty space, it may be separating us from entirely different worlds. If these bubble universes exist, they may not always remain isolated. In some models, they can grow, expand, and even collide. This idea sounds extreme, but it comes directly from the mathematics of inflation. As different regions of space inflate and form their own bubbles, they do not always stay perfectly separated. If two bubbles expand toward each other, a collision can occur. Not a simple impact like objects in space. This is a collision between entire universes. The energy involved would be enormous. The structure of space and time in both regions could be disturbed. Waves of energy could ripple through the newborn universe, and if such an event happened in the early stages of our universe, it could leave behind traces. Subtle traces, but detectable. Scientists believe these collisions could leave imprints in the cosmic microwave background. That ancient light acts like a record of the early universe. It carries information about conditions from billions of years ago. If something unusual happened, it might still be visible in that signal. Researchers have searched for specific patterns. One of the main targets is circular features, smooth, ring-like shapes that stand out from the random fluctuations. These circles would represent regions where the energy from a collision altered the temperature and density of space. Several studies have claimed to find hints of such patterns. Observable studies have claimed to find hints of such patterns. Unusual alignments, structures that do not fit perfectly with standard predictions, but the results remain controversial. Some scientists argue these features can appear by chance. Others believe they may point to something deeper. The difficulty lies in the data itself. The cosmic microwave background is extremely complex. Tiny fluctuations can overlap and create shapes that look meaningful. Separating real signals from random noise is one of the hardest challenges in cosmology. Even so, the search continues. Advanced missions have mapped this radiation with incredible precision. Satellites have measured temperature differences across the entire sky down to very small scales. Each new data set allows scientists to test these ideas with greater accuracy. There's also another possibility that adds tension to this theory. A collision might not leave a clean, obvious mark. It could create distortions that blend into the background. Slight shifts in temperature, small deviations in structure, effects that are difficult to isolate but still present. This means evidence of another universe could already be hidden in the data, unnoticed or misunderstood. If even one clear signature were confirmed, it would change everything. It would mean our universe is not alone. It has interacted with something outside itself, something beyond our observable horizon. A separate region of reality that once came into contact with our own. That would be the first direct evidence that other universes are not just theoretical ideas. They are physical entities. And it would raise an even more unsettling possibility that our universe has a history we cannot fully see. Events that happened before the earliest light we can observe, interactions that shaped its structure long before galaxies formed. The cosmic microwave background would no longer be just a snapshot of our universe. It would become a record of encounters, a faint memory of collisions that occurred at the very edge of reality. And if such interactions are possible, then the boundary of our universe is not as isolated as it seems. Even with the most powerful telescopes ever built, there is a limit that cannot be crossed. Modern instruments can see galaxies billions of light years away. They can detect faint signals from the early universe. They can measure tiny variations in temperature and structure with extreme precision, yet none of this allows us to look beyond the cosmic horizon. That boundary remains absolute. No matter how advanced technology becomes, light from beyond that horizon will never reach us. It is not a problem of sensitivity or resolution. It is a fundamental limit set by the nature of space and time. This creates a strange situation in science. Researchers trying to understand a reality that they cannot directly observe. They are forced to rely on indirect evidence, subtle signals, mathematical predictions, patterns that may hint at something larger but never fully reveal it. The deeper scientists go into these questions, the more uncertain things become. When they attempt to study the earliest moments of the universe, even the laws of physics begin to lose clarity. The period before inflation is especially difficult. Conditions were extreme, temperatures were unimaginably high, energy densities pushed beyond anything that can be recreated or tested. In that regime, the known laws of physics start to break down. General relativity, which describes gravity and the structure of space, no longer works cleanly at those scales. Quantum mechanics, which governs particles and small systems, also struggles to describe the entire universe at once. Scientists are left with incomplete tools. They try to bridge this gap with theoretical models. These models are built using advanced mathematics. They explore possibilities, they predict outcomes, but they are not directly confirmed. Many ideas about the multiverse, inflation, and cosmic origins come from equations that extend beyond tested physics. This does not mean they are wrong, but it does mean they exist in a space between science and speculation. There are also limits built in observation itself. Every measurement we make depends on light or signals reaching us. Every experiment depends on conditions we can control or detect. When something lies permanently outside that range, it becomes difficult to test in the traditional sense. This raises deeper questions. How much of reality can science truly access? Is it possible that some aspects of the universe will always remain hidden, not because they are complex, but because they are fundamentally unreachable? Some physicists argue that science should only focus on what can be tested. Others believe that mathematical consistency and indirect evidence are enough to explore these larger ideas. This debate is ongoing. It touches on the very foundation of knowledge. It challenges the idea that everything in the universe can be measured, observed, and explained. It suggests there may be limits, not just to technology, but to understanding itself. There's also a quieter implication. If the universe extends far beyond what we can see, then our picture of reality is incomplete by definition. Every map we create is partial. Every theory is based on limited view. The observable universe becomes a kind of sample, a region we can study in detail, while the larger structure remains unknown. Some estimates suggest that the total universe could be vastly larger than the observable portion, possibly so large that the part we can see is almost negligible in comparison. If that is true, then most of existence lies beyond our reach, not hidden by distance alone, but by the very structure of reality. And as scientists continue to push these boundaries, they are forced to confront a possibility that feels both humbling and unsettling, that the universe may be far greater than anything we can ever fully explore. The observable universe feels vast. It contains billions of galaxies, each filled with billions of stars. It stretches across distances that are almost impossible to grasp, and yet everything we have explored in this video leads to one simple truth. This is not the whole universe. It is only the part we can see. Beyond that cosmic horizon, space does not end. It continues in ways we may never directly observe. The edge is not a boundary, it is a limit on our vision. And right at that limit, strange clues begin to appear. Unusual patterns in ancient light, alignments that should not exist, signals that do not fully match our expectations. These are small details, easy to dismiss at first, but together they point towards something deeper, something beyond. Theories now suggest that our universe could be just one region in a much larger structure, one bubble among countless others. Entire universes may exist beyond our reach, each with different laws, different histories, and different outcomes. Some may never form stars, others may collapse before they begin. And in some cases, these universes may not be completely separate. They could interact, leave faint marks, subtle traces hidden in the oldest light we can detect, or it may not be other universes at all. It could be new physics, unknown forces, gaps in our understanding that we have not yet filled. Either way, the implication is the same. Reality is bigger than we thought. And more importantly, our knowledge is smaller than we assumed. Science has taken us further than anyone could have imagined just a century ago. But at the edge of the observable universe, we are reminded of something important. There are limits to what we can see, limits to what we can test, and possibly limits to what we can ever fully understand. The biggest discovery may not be what lies beyond the edge. It may be the realization that we are only seeing a small piece of a much greater reality. If you found this idea fascinating, consider liking the video and subscribing to the channel. There is much more to explore. And the deeper we go, the stranger it becomes.